Have you ever seen one of those incredible AI images and just wondered, how? How can an AI take a photo of a summer day and just like that, turn it into a winter wonderland? Or maybe even crazier, turn a regular horse into a zebra? Well, today we're pulling back the curtain on CycleGAN. It's this really clever piece of AI that figured out how to translate images, even when it has no direct guide to copy from. And this quote right here, it nails exactly why CycleGAN is such a big deal. It gets right to the heart of the matter. It solves a problem that stumped AI for a long time. What do you do when you just don't have perfect before and after photos to learn from? This is the massive challenge CycleGAN was built to conquer. So to really get our heads around this, here's our game plan. We're going to start with the problem itself, why this is so hard. Then we'll cover the absolute fundamentals of how an AI thinks. After that, we'll dive into the competitive game that makes all of this work, and then reveal CycleGAN's brilliant round-trip solution. And finally, we'll look at what it's great at, where it falls short, and the legacy it's left behind. Okay, so let's dig into that first big hurdle. Why is it so ridiculously hard to teach a computer to translate a photo of summer into winter? It sounds pretty straightforward to us, but for an AI, it's a huge challenge without the right kind of data.
I mean, think about it for a second. If you wanted to teach an older AI to change a day photo into a night photo, you'd literally need two pictures of the exact same place from the exact same angle with everything in the exact same position, just taken hours apart. That's called paired data. And in the real world, it's almost impossible to find. You can't take a photo of a horse and then a second paired photo of that same exact horse magically transformed into a zebra. It just doesn't exist. And that was a massive roadblock.
Right, so before we get to the big solution, we gotta lay some groundwork. We need to understand the absolute basic building blocks of an AI. And I know, this can sound super complex, but we're gonna break it down to the simplest possible piece, a single artificial neuron. It all starts with biology. On the left, you've got a neuron from a brain, right? It gets signals, and if they're strong enough, it fires a signal of its own. Now, look at the right. That's the AI version. It's basically a mathematical model of the real thing. It takes in numbers as inputs, multiplies each one by something called a weight, which is just a way of saying how important that input is, and then it adds them all up. Simple, but incredibly powerful. So the neuron gets all these signals and adds them up into a single number. But what then? How does it decide if that signal is worth passing along? Well, that's the job of the activation function. You can think of it like a light switch. If the total signal is strong enough, it flips the switch to on and passes the information to the next neuron. This little switch is what lets the network learn all the complicated, messy, non-linear stuff in the world, not just simple straight lines. It's absolutely crucial. Okay, the network makes a guess. But how does it know if it did a good job? That's where the loss function comes in. It's basically a scoring system. It looks at the network's output and compares it to the correct answer, then spits out a number that measures how wrong it was. You can call it an error score or a loss score. The entire goal of training, the whole point of the exercise, is to tweak the network to get that loss number as close to zero as humanly or, well, computationally possible. And how does it get that score lower? It uses a process called gradient descent. The best way to think about this is to imagine you're standing on a giant, hilly landscape in the dark, and your goal is to get to the lowest valley. What do? You feel around with your foot and take a small step in whatever direction goes downhill. That's exactly what the AI does. It calculates the slope of the error and adjusts its internal weights, taking tiny little steps in the steepest downward direction. It keeps doing this over and over until it settles at the bottom of the valley, the point of lowest possible error. That, right there, is the essence of learning in AI. All right, now that we have the basics down, we get to the really cool part. The technology that underpins all of this is called a generative adversarial network, or a GAN. And it's not just one AI learning by itself. It's two AIs locked in a head-to-head competition, a sort of digital game of cat and mouse. It's best to think of them as an art forger and a detective. On one side, you have the generator. That's our forger. Its whole job in life is to create fake images that are so good, they're indistinguishable from the real thing. On the other side, you have the discriminator, our detective. Its only job is to look at any given image and call it out. Is this a real photo or is it a fake cooked up by the generator? And this is where the magic happens. They're trained at the same time, constantly trying to one-up each other. Every time the discriminator spots a fake, the generator gets that feedback and learns how to make a better forgery next time. But every time the generator manages to fool the discriminator, the detective has to get smarter and learn what to look for. This goes on for millions and millions of rounds. They both get better and better until the generator becomes a master forger, creating images that are incredibly realistic. Okay, so we've seen how GANs can make photorealistic images, but that doesn't solve our original problem, right? How do we control what it generates? How do we tell it to turn a horse into a zebra, specifically, without those paired examples? This is where the genius of CycleGAN finally comes into play. This really is the million-dollar question. How does a machine learn the fundamental style of a Monet painting and then apply it to a regular photo if it's never seen that exact photo painted by Monet before? How does it know to change the pattern on a horse to stripes, but keep the overall shape of a horse? The big idea, the core intuition, is just beautifully simple. It's a concept called cycle consistency. And this analogy says it all. If your translation from English to French is any good, then when you translate it back from French to English, you should get something really, really close to your original sentence. That's the aha moment. And here's how CycleGAN puts that idea into action with what it calls a round trip. Let's walk through it. First, you start with an image, say a horse. A generator, let's call it G, does its best to translate that horse into a zebra. Now here's the clever part. A second generator, we'll call it F, is trained to do the exact opposite, to turn zebras into horses. So we feed our newly created fake zebra into generator F and it translates it back into a horse. And for the final step, the AI compares that final horse to the original horse we started with. If they don't look almost identical, the whole system gets penalized. This round trip forces the generators to preserve the original content, not just make up a random zebra. So when you look at the whole shebang, CycleGAN is actually 4 different AIs all working together in this delicate dance. You've got your 2 generators, G and F, handling the back and forth translation. You've got 2 discriminators, one for each style, plain, detective, and it's all guided by different goals. The adversarial loss is what pushes the generators to make images that look real. The cycle consistency loss is the round-trip check that makes sure they don't change the content. And there's even a third loss, identity loss, which basically tells the generator, hey, if you don't have to change the colors, don't. So that's the beautiful theory behind it all. But what happens when the rubber meets the road? How does it actually perform in the real world? Well, like any groundbreaking tech, CycleGAN has some jaw-dropping strengths and some pretty important limitations too. And what it can do is honestly spectacular. These are the classic examples that really put it on the map. It's an absolute master at transferring texture and style, turning a photo into a Monet painting or a summer scene into a winter one. It's like it's repainting the surface of the image while keeping the structure underneath. And this isn't just for fun. This has real-world uses, and things like improving medical scans or creating tons of synthetic data to train other AIs. But it's not a silver bullet. It really struggles with major changes in shape. It's not going to turn a cat into a dog very well. It also has this limitation where, for one input, you only get one output, whereas a human artist could give you dozens of different styles. And of course, training 4 networks at once is slow and takes a ton of computing power. Since CycleGAN came out, newer models like CUT and Munit have been developed to tackle these exact issues, often finding clever ways to get similar results with a lot less work. So you might be thinking, is CycleGAN obsolete then? And the answer is a resounding no, not at all. Its central idea, that cycle consistency, is so simple and so powerful that it's still a fundamental concept in the world of generative AI. It's often the first thing researchers will try because it just makes sense, it's easy to implement, and we understand how it works. And that really brings us to the final, most important takeaway. CycleGAN's true legacy was a fundamental shift in how we think about these problems. It proved that you could teach a machine to translate between 2 visual languages without needing a perfect word-for-word dictionary. It opened up a whole new world of possibilities. And pretty much every advanced image-to-image model that has come since is, in some way, standing on the shoulders of that brilliant insight. And that's why, even today, understanding CycleGAN is so important.